Kepler was a pretty nice guy. Let's get him up here. Kepler studied enormous amounts of Tycho Brahe's initial data on the locations of planets, and he discovered the following facts. First, I'm going to make us an ellipse. So I'm putting a couple pins in, and then I'll let's step it out a little bit. No, I guess we're stuck with it because I've made that hole. Okay, so I'm going to make an ellipse, and it will be the pretend motion of a planet around a star. I'm just pulling out at the edge. Come on, keep working for me. Keep working. Okay, so here we have an ellipse, and these are the two foci of the ellipse. This focus and that focus. And Kepler's first law says that the sun is at one of these foci. So I'll give you a bright red star there. So 1, sun is at focus. All right, and Kepler's second law is the law that I like to call the windshield wiper law. Kepler's second law says equal areas in equal time. And in parentheses, I'll call it the windshield. The windshield law works like this. If you take the location of a planet at some moment in time, let's say it's a nice brown planet, and it's over here, and let's say that planet is going counterclockwise around the star, we could draw a windshield wiper from the sun to the planet. And in some amount of time, let's call it, I don't know, let's call it delta T1, the planet will have moved from here to here on its orbit, and so we can draw another windshield wiper out to the planet. And we could calculate, in principle, fairly easily, we could calculate this area that the planet has swept out with its windshield wipers. Now what we're saying is this area, which I'll call A1, coincidentally, if we look instead at the planet when it's over here. What do you want it to be? Still a brown planet? I guess that makes sense. Let's make a brown planet over here. If it's over here, it's actually going faster. And I can argue that in a couple ways for you later, but let's draw a velocity vector that looks more like that. That's its tangential speed at that moment. And we can do a little windshield wiper business right here. And the cool thing about Kepler's second law is he observed that for ellipses where the sun is at one of the foci, the area that's swept out in the same amount of time, let's call it delta T2, but then we'll make the statement that delta T1 equals delta T2. Let's see. If delta T1 equals delta T2, then A1 equals A2. That is Kepler's second law also. And I'll try to draw that for you. What we're saying is that this area is then a much broader area here because of the fact that it's going faster. So we'll shade in this area and call it A2, and we'll say that if delta T2 is the same time as delta T1, then those areas that the planet has swept out, that's the cool language about windshield wipers, right? Then that area that the planet has swept out is equal to the area it swept out over here. Now, he learned this by poring over tons of data, and he didn't have a computer, which I find incredibly respectable that he did this. So the Earth is, in fact, in an elliptical orbit around the sun, and that means that the Earth is going slower when it's farther away from sun, and faster when it's closer to the sun. This also makes sense because if you think about the gravitational pull on the Earth, let's think about two situations. We could put the Earth, now maybe we could do it with just one. Let's put the Earth right here. The Earth is right there, and I'm justifying Kepler's second law right now. The Earth is going this way, And the Earth is feeling a gravitational force this direction. That's the gravitational force on the Earth. Notice that the angle between the gravitational force on the Earth and the velocity of the Earth is larger than 90 degrees. That means that the Earth is slowing down. So if we were to resolve this into two components, let's resolve this force of gravity into two components. We could say that this force of gravity, this component of the force of gravity directly upward, is the centripetal force that's maintaining this turn, and the backwards component of the force of gravity is the component of the force of gravity that's causing this velocity to decrease. The tangential speed is decreasing because there's some force going back on it. If we do the same thing up here, imagine what it would look like up here. I think I'm going to just clutter this up to put planet up here. But imagine up here, it would be the exact opposite. The velocity is this direction, and the acceleration is down and in because the force of gravity is always pointing directly to the sun. So everywhere down here, let's just make a big teal nasty right here. Everywhere down here, speeding up. Nope. Perfectly wrong. Sorry, slowing down. Everywhere down here, the planet is slowing down, and everywhere up here, the planet is speeding up. Since the planet is slowing down here and speeding up here, it must be going the absolute slowest right in the transition, and it must be going the absolute fastest right here after all that time speeding up. Okay, fair enough. And then Kepler's third law is a beautiful thing. So let's see if we'll just plop down Kepler's third law, which he got simply from mathematically analyzing these enormous bits of data. He said T is proportional to R to the 3/2. Oh my goodness. And that means the same thing. T equals some stuff times R to the 3/2. So let's see if we can derive that, though. It's actually not that bad. Kepler wasn't able to do this, but Newton came along, what was it, 80 years later or something, and Newton says, this is Kepler's third. That was all that Kepler said. Newton came along 80 years later. Nah, maybe not 80 years. Maybe it was just 20 years later. Everybody had accepted this because the data showed this, and no one really knew why, and no one knew what that stuff was. So Newton, in order to get some street cred with his buddies, the old British men, and well, all the Academy of Sciences throughout Europe, and he said, check this out, guys. Here's the force of gravity. The force of gravity is, well, I'm proposing, this is Newton, I'm proposing the force of gravity is G times M1 times M2 over R squared. And I'm saying that the force of gravity is providing a centripetal force on stuff that's going around in a circle. So, for instance, if we put the sun in here, and we have a planet out here, we've got the sun and a planet, and the force of gravity is providing the centripetal force. So I'm going to say is providing or is equal to the centripetal force, which is, well, it's going to be m times v square over r, and that's the centripetal force, Fc. Force of gravity is the centripetal force. What the heck is that writing? There, Fc. Okay, so these things are equal, and this is Newton's key statement. As soon as he makes this statement, we're going to be able to do some math and prove Kepler's law. This is going to be pretty awesome. And without preparing, I'm just going to blob through it. Let's see what we get here. This R cancels that R right there. And we have to figure out what mass this is. Let's call this the mass of the sun times the mass of the planet. Is it the mass of the sun or the mass of the planet that appears in the centripetal force equation? Centripetal force is causing an acceleration. Oh, centripetal force. Well, that's just the mass of the planet times the centripetal acceleration of the planet, right? So the mass of the planet is what should go right here. And in fact, then the mass of the planet cancels out also. Yay! Watch this. The mass of the planet also cancels out. And we get this equation that then reads capital G times the mass of the sun divided by the radius of the sun is v square. Now, you remember that velocity. Do you remember anything about velocity? Recall that tangential velocity is, well, how far something goes is 2 pi r, that's circumference, and then we're going to divide that by period. So I'm going to plug this in. Ready? Right here. See what we get. And we'll see g times the mass of the sun divided by the radius. Ooh, what radius? What radius? Is this the radius of the orbit, or the radius of the sun, or the radius of the planet? We should specify that. That's the radius of the orbit. Okay, this equals 2 pi r divided by period, the whole thing square. So let's spread it out a little bit. We've got capital G times the mass of the sun divided by the radius is 4 times pi squared times r squared divided by period square. I'm going to solve this for t squared. Seems like t squared is going to be equal to, let's see, we've got 4 and pi squared and r cubed. Then we're going to divide it by, we have to divide it by capital G and the mass of the sun. Notice what this equation says. It says t squared equals 4 pi squared over g times the mass of the sun times r cubed. Oh, dang! Newton came up to them after this, 3 minutes of work, and he said, I got your constant of proportionality right here. That's the stuff. And they plugged it in on their TI-89s, and they said 4 times pi squared, and they divided by Newton's gravitational constant, which he'd provided for them in the force right there, and the mass of the sun, which had been calculated in an awesome way also. And they found that to be equal to that stuff for all the planets. And Newton was in. Socially, he blew it away. One, sun is at focus. All right, and Kepler's second law is the law that I like to call the windshield wiper law. Kepler's second law says equal areas in equal time. Let's step it out a little bit. No, I guess we're stuck with it because I've made that hole. Okay, so I'm going to make an ellipse, and it will be the pretend motion of a planet around a star. I'm just pulling out at the edge. Come on, keep working for me. Keep working. Okay. So here we have an ellipse, and these are the two foci of the ellipse. This focus and that focus. And Kepler's first law says that the sun is at one of these foci. So I'll give you a bright red star there. So Kepler was a pretty nice guy. Let's get him up here. Kepler studied enormous amounts of Tycho Brahe's initial data on the locations of planets, and he discovered the following facts. First, I'm going to make us an ellipse. So I'm putting a couple pins in, and then I'll and in parentheses, I'll call it the windshield. The windshield law works like this. If you take the location of a planet at some moment in time, let's say it's a nice brown planet, and it's over here, and let's say that planet is going counterclockwise